Hello, my name is Ethan, and in collaboration with Spencer and Zach, we made a project for our Introduction to Particle Technology class, and we constructed a hydrocyclone separation process. Now, what is a hydrocyclone? A hydrocyclone is a separation device that uses swirling flow to separate heavier particles from a fluid. When liquid enters tangentially, it spins rapidly, creating a vortex. Heavier solids are forced outward and downward to the underflow, while the cleaner liquid spirals upward and exits through the overflow. Hydrocyclones are simple, compact, and operate with no moving parts, which makes them highly reliable for continuous separation processes. And over here, I just have a diagram listed of a hydrocyclone. And as you can see, it has the clean liquid overflow on the top and the thicker particles coming out at the bottom. Now, the applications of hydrocyclone. In industry, hydrocyclones are used everywhere that solid and liquid separation is needed. In mining, they classify ore particles by size, removing unwanted fines, and help improve downstream grinding efficiency. In wastewater treatment, cyclones remove sand, grit, and suspended particles before biological or filtration stages. Their ability to handle large flow rates, resist abrasion, and operate continuously make them essential in these sectors. To drive fluid through a hydrocyclone, a pump must apply enough flow and pressure to create the vortex. Our project used a progressive cavity pump, which is listed here on the top, and this moves fluid through it using a rotating helical rotor. These pumps are great for handling slurries gently and at steady flow rates, but they typically operate at lower pressures. In contrast, the centrifugal pumps here listed on the bottom are industry standard for hydrocyclone systems because they can generate the high flow and pressure required to sustain efficient cyclone separation. Now we will be watching a video of how we prepared our experimental trials after constructing the process.
To prepare for the trials, different aggregate sizes will have to be dumped and agitated into the source tank to create a desired slurry. In the first clip, a finer aggregate is shown. This is the slightly larger size distribution than the finest aggregate being shown now. These particles are a little bit smaller and not quite as large. Next, you will see the aggregates being dumped into the source tank. The source tank is where the aggregates will become suspended in the liquid, so that they can be pumped through the system. In the system, the hydrocyclone is powered by the progressive cavity pump as seen in the video. Finally, the finer aggregate is dumped into the source tank as well as the finest particle size for the trial preparation and for it to be conducted. In this diagram, you see the simple setup of the actual hydrocyclone system, assembled in the unit operations laboratory. Both of these unit operations were donated to the University of Reno by Lithium Americas. As listed, the source tank is where aggregate is mixed by agitation and then pumped tangentially to the cyclone inlet using a progressive cavity pump. The bypass valve exists to regulate flow and maintain pressure when needed, acting as a release system in the process. The truncated cyclone has two outlets. The outlet on the bottom, also called underflow, is where denser solids are recovered. The overflow return is where water and lighter or finer particles are recycled back into the source tank, although not listed, process powered by manually plugging in the progressive cavity pump to an electrical outlet. After agitating the slurry, the pump is powered and bypass flow is used to further circulate and stir the tank. Once the solids are fully fluidized, the bypass valve is closed, allowing flow to enter the system. The outlet stream provides an indication of system performance by monitoring the flow pattern. A ropey, semi-spray appearance, as seen here, is optimal and indicates the solids are freely existing. The overflow consists primarily of the carrier liquid, with only small amount of fine particles being present.
No solids. Perfect.
In this clip, you see the aggregate becoming suspended in the actual source tank. Next, you see the outlet stream, what actually comes out with the different sized particles and how they are distributed. The next step of the process is shown now. It's the sieve machine. The sieve machine has different tray sizes to allow for the distribution to be created. These can be seen more clearly in the following diagram. The different trays have mesh in them, which allowed particles of different sizes to get through. This is how we can create the particle distribution. The largest sieve tray we used was a number 8 mesh, which has an opening of approximately 2.4 millimeters. And then the smallest we used was a number 50 mesh, which has an opening of approximately 300 microns. The sieve tower we chose is lying on an auto siever that vibrates the tower to filter out the particles that were collected during the previous steps.
So dry. All dry.
By running the collected solids through various mesh sizes, we can determine the particle size distribution. During operation, the sieve gently shakes, allowing particles to fall through the appropriate meshes.
Dippin' dots, yeah.
After sieving, the collected material is analyzed, providing a clear picture of particle size distribution.
I'd like to end off this video with some references and acknowledgements. The first two references being the specification sheet for both the Hydrocyclone and the progressive cavity pump. The last reference there being a textbook from Rhodes, which we used for our theory behind the project. Some acknowledgements are Dr. Sage Heibel, our project supervisor, Brian Nagy, a technician at UNR who helped us with the manufacturing side of the project, Ryan Revenell and Devron Gonzalez from Lithium Americas who supplied the unit operations, and Mike Kavistik who supplied the unit operations laboratory where we assembled our project. Thank you, and I hope you enjoyed our informational video.